Okay. Okay, so we are about to start. Yes, I hope you see me now. So thank you for joining our AI testing talks. And today we start a short sequence of 3 lectures on anomaly detection. And okay, speaker is Rostislav Yavorski, it's me, I'm from Exactpro. And today's lecture will be the simplest one. I will try to be very clear, very introductory, because okay, just for everyone to understand how anomalies are important, why we should find them, why should we detect them, and why this is very useful in very different domains and application areas. So okay, let's start from definition. And okay, anomaly, usually it's called anomaly, sometimes it's called outlier, some people call it novelty in different contexts, and possible definitions are listed here. So anomaly is data points, events, or some observations that deviate from normal behavior. And this is, you can see this nice illustration from our designers on the right. So you see sequence of lamps, and each lamp is like black and white, and they are almost the same. Actually, they are all the same size, the same direction, and at some points you see completely different object. So this is anomaly. This is outlier. So it has different color, different direction, different size. So it definitely deviates from normal behavior. So the other definition, it's instance or collection of data that occur very rarely. So you see this lamp is unique here. So we assume that anomaly is something which is not appears like every second and quite frequent. So it's quite very rare object. And the other definition is observation which appear to be inconsistent with the remainder of the data. And again, you see this on this picture that somehow this outliers, this anomaly it doesn't conform to the internal logics of the other series. So this is a definition of anomaly. So here's another picture. You see here 4 different figures, and on the left there is a list of different challenges. So the first challenge that in order to define abnormal behavior, you need first to have the definition of what's normal. And in real applications, that's really not easy to define what's normal. So you see on this picture, the figure number 1 is you see the blue circle on the top, and then a black triangle, and the second triangle is different color, and the circle is black, and another figure, instead of triangle you have different figures, but according to my feeling they're definitely all different, but none of them is not really anomaly. So everything is something within the normal definition, but again it depends on your context. So second, that noise data are not anomalies. So in real life you never have the same objects. So something is different, some parameter could change, but noise is not really what we call anomaly. So the third challenge is the definition of anomaly is domain specific, right? So if you're speaking about geometric figures, that could be one anomaly. It could depend on, for example, dimension or some other properties. If you're speaking about some software engineering, software quality assurance domain, then anomaly definition could be completely different. If you work, for example, in some medical applications, then again, in order to define what's anomaly, you should really understand your application domain. So the other challenge is that anomalies evolve over time. So if you speak about some live system which is not static, then for example, some behavior during this day could be anomaly because you did not observe this, for example, before, and the next day that could be completely okay. Consider something just simple weather observation. So So assume today is the summer and you have like hot weather and green grass and everything, and you write down some observation, and at some point you get snow. Definitely snow during July would be an anomaly. But then day after day, summer is ending, then you shift to autumn, then winter, and during the winter, surely snow is not anomaly at all. It's something which you have every day. But on the other hand, the hot weather during the winter definitely is anomaly. So you see, so the definition of anomaly is not that easy. It depends on domain, it depends on time, and okay. So why do we need to search for anomalies? And there are two different scenarios. So in some areas, you search for anomalies just to discard them, because anomalies are kind of waste data. And different examples are here on the slide. So first of all, it's about statistics. And we'll see this example just in a couple of minutes. So when you try to describe some data set, then you compute some average values, some standard deviation, and if this data has some anomalies, outliers, then all this computation will be spoiled. And another similar application is machine learning. Again, you use different training data to teach your algorithm, to teach your system how to apply to make some decisions. And in this context, anomalies can really be not something good. So you search for anomalies, you detect them, and you discard them to make your data set more clean, more useful. But there are different applications when you search for anomaly as something very useful. For example, you are working as a bank analyst who are looking for fraud detection, and you have a huge amount of different data, different customers, different scenarios, different logs, etc. And once you found some anomaly behavior, it is exactly the most valuable data for you. This is exactly what I'm looking for. Now you understand, okay, now I see this guy is not really a good guy. We need to do something this, and this behavior is kind of not normal behavior. Similar situation is, for example, in different medical applications. And assume you are a doctor and you see a patient who has some problems, and you have a lot of analysis, like data, what's going on with this and that, and you need to figure out the reason what's the reason of this illness or of this weakness, whatever. So, and once you found this anomaly, this is really the valuable part for you. So this is something you are looking for. So you see, sometimes we look for anomalies just to discard them. In other examples, anomaly is actually what we really need from this huge amount of data. Okay, and during the rest of my lecture, we'll go through several examples more deep way, just to give you better understanding. And the example number one is from statistics, and it's about computing mean and standard deviation. This is really very simple, but very important example of anomaly, just to give you the feeling, the understanding what is anomaly, what is outlier, and how this anomaly, how this outlier can change your kind of perception of data. So why this picture? Because statistics, okay, some people have profession of statistician or data scientist. Definitely they work with statistics daily. But even if you are just have completely different profession, then anyway, you count your money, you think about your house, your children, your life, and in every application, in every situation, usually have a lot of different data. For example, about your income, about your spending, about your kind of whatever. So internally, in our mind, we always apply statistics just to to make it simpler. So instead of keeping in mind like 20, 200 or several or even more numbers, usually we just compute some average value and work with it because it's much more simpler. And okay, so let's see, for example, following example. So assume you are a team leader or a business owner, and you have some team members. They are listed on the left, like Maria, Jose, Ahmed, Anna, Carlos, Patricia, and this table is about salary. Don't care about which currency is it. So you see some people earn like 41, some people have 44, 46, and again, it's quite difficult to remember all these numbers. So you ask your analyst to compute what's really the mean value and what's the standard deviation. And the formula is quite simple. You compute the sum and divide it by 6. So you see that the mean salary is 44 and deviation is 1.4, which make perfect sense. So you see that Ahmed is the one who gets this exactly the salary. So there are some people, Jose, Anna, and Carlos, who earn a little bit more, a little bit less, and deviation is exactly 1.4. So you're feeling okay that when analysts show you this data, you understand that some people in your team earn 44 or something like that, and the other earn maybe slightly more, but not that big a difference, like maybe 44, 45. And some other people earn slightly less, which is like 43, 42. And it's exactly what you have in your table. So this computation makes perfect sense and completely corresponds to our intuition and what's mean value and what's standard deviation, right? And what's going on next? So you hire some intern, some student from nearby university who is like, okay, working part-time maybe and has no experience. So this Jersey intern agrees to work for 9. And okay, and then analyst recomputes the values. From now, the mean value becomes 39. You can easily recompute, just repeat this computation. And standard deviation becomes equal to 12.3. And assume that, again, that you are this business owner who orders this analyst to compute this number. You look at these numbers, and in fact, they are completely misleading. Because again, you expect when you see that the mean value is 39, that probably some people in your team earn 39, maybe some people earn slightly more, like 40, some other earn less, like 38, 30, 40, maybe 36. But actually, there is not a single person with salary 39, and no one with salary 40, and no one with salary 38. So this data becomes kind of meaningless. And the values you computed are really hard to interpret. And why? Because you have this outlier in your data. So according to the definition, outlier or anomaly is a very rare value, and it's exactly what you have here. So 9 is not typical value in this data set. So, and presence of this outlier of this rare value makes your statistics, you see, much less valuable and much okay, really hard to interpret. And this is a very important example, as I mentioned, because it shows you that just one value, one number in your data set will make this quite serious change in the result. And that's you always need to have in mind this kind of example, that anomalies and outliers are very important. Okay, I hope this is more or less clear. That was very simple, as I mentioned, but very important example. Well, let's go ahead, and in this section we'll speak about simplest way of machine learning algorithm, which is called linear regression. And consider this kind of example. So again, we are speaking about business context, and you have different people performing different tasks. As you see on this picture, tasks are actually almost the same. So the first person works with red cubes, the other with green. So we expect that there is some kind of average time you need to perform this task. And usually you need some maybe overhead in the beginning of your working day at the end. So this is a good example where you could apply a linear regression to compute the average time and the overhead time. So let's see the table. So you performed some measurements and recorded them here. So if a person is asked to make 2 units, then it took him or her 14 minutes. 4 units, then 19 minutes, 6 units, 30 minutes, etc., etc. Then you apply linear regression. You see this green line, which quite good approximation of time you need to perform this kind of task. And you can use this linear approximation for future predictions, right? And you see that according to this algorithm, the average time you need for 1 unit is 4 minutes. And overhead, like in the beginning or at the end of the work, just to start your system, maybe some other preparations, it takes you approximately 5 minutes. And then we compute approximate error, and you see that expected error is again rather small, which is good. So you predict that average time for 1 unit is 4 minutes, and the error is like 0.3, which is less than 10%, which is quite good, right? And the prediction for overhead is 5.3, and again, estimated error is rather small. But then you got, now you know this term outlier. So you asked your employee to make 3 units, and the time it required turned out to be 41 minutes. And that could be for different reasons. For example, someone called him maybe from some urgent call, or maybe something happened, maybe you don't know. But surely this measurement is some kind of non-typical here. So, but let's see what happens if you just don't care and apply the same algorithm. So you see the line, which is now of this color, is not that good. I mean, in terms of approximation of these data points. Then the computation says that the average time for 1 unit is 2.7 minutes, and overhead is 16. And even more, if you try to compute the quality of this prediction, the estimated error, you see that estimated error is 1.5, which is really huge. So assume you come to your boss, say, okay, you made all the measurements, and the boss asks you, okay, what's average time for 1 unit? You say, okay, that it could be probably 1, something 1.2 is possible, 2 minutes also possible, 3 is also possible, and even it could be 4 minutes. Yes, 4.2 is also possible answer. So you see, this is kind of very poor prediction. And again, for the other parameter, the value could be like 7 is okay, 15 is also possible, and 25 minutes is also possible answer. So you see, the quality of your machine learning model is really poor. And why? Because you have this inconsistent observation in a data set. So if you really would like to apply this this prediction, this performance analysis in your future work, you would spend some time to figure out that this observation, okay, this is, if you just from common sense, you see that it takes less time, just 19 minutes, to make 4 units than to make 3. So definitely there is some error here, and I would suggest you maybe either just to remove this measurement or just to repeat it, but definitely before this decision, you need to figure out that you have this inconsistent measurement, this inconsistent data in your data set. And this is exactly what we call anomaly or outlier. And this example and previous one was about kind of negative examples of outliers. But as I mentioned, there are quite positive examples. And let us go to the third section, which is called fraud detection. So, right, this picture, I like it because it's very clearly explains what's going on. So you have some amount of money of something on your credit debit card, and we are all happy with all its electronic payments, etc. But definitely there are some risks, and unfortunately, some people try to use all these vulnerabilities and system imperfection just to steal your money. So let's start from definition. What's fraud? Fraud is actually a criminal behavior. So it's a deliberate act of aim at obtaining unauthorized benefits. And here are some examples of fraud. So if someone is just theft of funds or forgery of some documents or payment which was not authorized by stakeholders, or some wage which were not earned, and another example is identity theft, which another quite unfortunately wide example of fraud. So surely this is not something new. For years, criminals tried to do all this. So there are some already indicators. How can we find out that something like that is going on? And let's see this list of indicators. That the first one is excessive number of checking accounts. So look at this first word, excessive. Excessive means something really not typical, right? So bigger than usual, right? So you see, there are kind of implicitly, you see already the definition of outlier or anomaly in the definition of fraud. So another indicator is frequent changes in banking accounts. Again, frequent means something more, something rare, right? Something not normal. Okay, number 3, behavioral changes, and number 4, lifestyle change. So again, we are speaking about changes, so about something which is not normal. I mean, normal from observation, from data analysis. So you see that all indicators actually about some deviation from normal behavior. So all the algorithms and methods and tools which we have for statistical and other types of anomaly detection and outlier detection could be successfully used for this kind of applications. And okay, today we'll not go into details, but definitely I plan to have a lecture on this topic separately. So you see, there are kind of 2 different approaches to fraud detection. And the first one on top is called rule-based, and it was applied like for many years. And the idea is quite simple. So you had some fraudster who commits some fraud, then you have an analyst, a human, who analyzes this behavior and formulates some specific rules. And then the rules are used for every kind of, not every, like inside this bank or inside the organization, the rules are used to detect all this fraud. So the traditional approach is about analyzing activities from past behavior. So you already have example of what fraud is, and then you use this example to find out the other similar behavior. And the other approach, which is quite popular currently now, is about applying machine learning. So again, so you have a lot of kind of number of users, customers of your, for example, bank, who perform different transactions. Then you use this data, this information, to train your machine learning model. you see. So on the first approach, the key point is human analysis, but for the second approach, you have a machine learning model, which is trained automatically, or maybe not completely automatically, which it could be supervised learning with some participation of analysts. But anyway, you use this machine learning model then to detect anomalies, to detect the behavior which is not kind of typical for your customers. And then what's better about machine learning, that even if someone designed some new fraud scheme, which was never used in the past, at least for this organization. So you don't have any example, you don't have any data about like this kind of behavior in the past. Anyway, machine learning can show that this behavior is not typical, that this is outlier, this is anomaly. So you can have a look, a closer look on this example and find this fraud even without similar examples in the past. So that was right example when you're looking for the anomalies, because the anomalies is actually the most valuable part for you as a fraud analyst. Okay, let's go to another example, and I already slightly mentioned it. It's about medical diagnosis. And again, this is a typical example of medical image. And okay, for professionals, it definitely provides a lot of information. But what's specific for medical application, that there are no two people who are actually identical. Everyone is different. Some people are tall, some people are not, some have, okay, whatever. So, and there are no kind of, so this is exactly the example of domain where it's very difficult to define what is anomaly. Because for some people, this is could be treated as anomaly, but for other, definitely you can find other people with actually the same characteristics, the same parameters, I mean, of this particular image probably, or something else. And for those people that it will completely normal. For example, like could be a guy who doing sport, or the other guy who has a completely different lifestyle. For them, definitions of normal or anomaly will be completely different. Okay, so what's the goal? The goal is of this medical diagnosis approach is to capture unique characteristics of the physiological data that could offer you additional, very important, very specific information about the patient. And again, this is a huge topic, the huge area. A lot of research is done here, and surely that deserves maybe a separate lecture, or maybe even the whole course. Today, I just want to show a nice picture from publication about opportunities on machine learning to improve surgical ward safety. And you see, the idea is that the physiological data could be combined with data which you gather from different variables, and also with streaming electronic health records. So you have a lot of data which could be collected about this particular person. Then you apply modern machine learning technique in combination with clinical assessment from professionals, and then this data could be used on the other stages for early recovery and rehabilitation or whatever. So again, this is a very important topic, but what we have here, again, a part which is related to different methods and algorithms for anomaly detection, for outlier detection, and that's really important here. Okay, and let's return back to engineering. And the last example today is about fault detection. And this picture is just to help you to dive into the context. So modern technical systems, engineering systems, doesn't matter if you're speaking about construction engineering, software engineering, hardware, whatever, software, the systems are very complex. So you see, you have a lot of different parts, different modules. They are somehow connected, interconnected, and some of them are new, some of them are outdated. You have some legacy parts, some brand new parts, and it's really difficult to maintain, to upgrade that kind of systems. And as a matter of fact, regularly you get some faults. And the problem is that it's quite easy to see that there is some fault in the system. For example, you see that something's going wrong, but it's not that easy to figure out where this fault, what is the reason, what is the cause of this fault. So fault detection is about monitoring a system and identifying when a fault has occurred and to figure out the location, right? You need to, in order to fix something, maybe to replace some parts, some details, you need to figure out what actually was the source of this fault. And this is exactly where all this data analysis and anomaly detection could be useful. And this scheme is from another source. You have this link on the slide. So if you are interested in this kind of application, you can go deeper and study it in more details. But let's see just the main steps of fault management systems. You see, first it starts with descriptive analytics, and it's very similar to the other applications. You have some historical data which helps you to define what's really normal, what's really okay. Again, definitely you will have a lot of noise, different deviations which are quite within the definition of normal, but having this historical data allows you to define and precisely measure all these parameters and all these distributions. Then with this historical data, you can perform some diagnostic analysis and study some trends. And then with these trends, you can do already some predictive analytics and use this analytics to figure out what was really wrong and what are faults. So we see completely different application area, completely different systems, completely different tasks. But again, what you need from data analysis is to figure out what was kind of not normal. So to conclude today's lecture, let's go back to definitions. So as already mentioned, there are two similar terms which are used in this context. The first one is outlier, and the other one is anomaly. There are no clear difference. So usually we speak about outlier when it's data point. Usually it's about rather small dimension systems. So if your system could be described like about one parameter or two parameters, and then you see that this parameter is kind of different, it deviates from normal, then we call it usually outlier. But anomaly, again, very similar term. Formally, there are patterns in data that do not conform to well-defined notion of normal behavior. So usually this term is used if your system is very complex, you have like thousands of different parameters and not single one is responsible for this deviation. So you have like different pattern, different combination of your parameters, which result in your anomaly. Then this is called anomaly. But again, you can use the both terms interchangeably. And maybe the most important slide, let me just repeat it, is that in order to define what's anomaly, you first need to define what's normal. And this is very difficult because, again, you always have some noise, some differences, and noise is not anomaly. Second, it's really important to know, to understand your application domain. because anomalies are always domain specific. And the third, that anomalies evolve over time. So what was okay today, it could be anomaly tomorrow and vice versa. And the last point, it would be really kind of dream to have like checklist. Okay, for our systems, we have this kind of possible anomalies. Number one, number three, and then you just go through, check it. Unfortunately, it's not possible. Okay, maybe sometimes, but usually this is not possible because too huge number of different possibilities. What could go wrong? What could be kind of not normal? So you never have this checklist. So you need to apply some advanced techniques from statistics, from machine learning. And this is exactly the topic of our second lecture, which is planned for the next week. So welcome to AI Tasting Talks. Okay, let's check for some questions. But it's okay to ask even later when you see this recording. So I see some of the questions, but some of them will be answered exactly during the next lecture, and probably we'll organize a separate question and answer session just to answer this. So I suggest to finish today. So thank you again, and looking forward to see you on my second lecture, which will be on statistical methods for outlier and anomaly detection. Thank you.